Welcome on the session that will be focusing on the cohesive surface traction. Mostly linear damage evolution law will be discussed at this session, and that will be related to the ABAQUS. My name is Lucas, and I'm a computational validation engineer in company ID Aesthetica, mostly focusing and concentrating on the um, concrete and the steel connections, concrete discontinuity, the region design, and anchoring design. Maybe you know me from the webinars and from the trainings. So that's been something about me. I have structural and the mechanical engineering background, so um, I do believe that I will serve you some good content. What about the agenda that we'll discuss today? So actually, I'll be coming out from the CEB-FIB Model Code 220, where it's very well described how the bond slip behavior in between the concrete and ripped reinforcement rebars works. We will focus also on or create some testing setup, or explain at first some testing setup, uh, like say some preassumption about the cohesive contact properties, and also some what is it basically, what imagine behind the cohesive surface traction and linear damage evolution law. So based on the needs of every structure engineer, they wanted to get deeper, understand all the equations. So that's very important to know how this scalar as a damage has been like created or derived um, from this constitutive law. So we will do step-by-step derivation of linear damage evolution law to explain how it works, to have like a proper wisdom for insert into the ABAQUS. And in the next session, there will be discussing and mostly modeling in the ABAQUS to get the results and also input all the properties that will be discussed today. Perfect. So I will just turn off my camera and we can move forward. Um, we can just move forward to CEB-FIB model code, how it's been listed there, and what failure modes can occur um, once the reinforcement rebars is embedded in some volume of the concrete. So once we are like investigating the bone slip behavior, you can experience like a two failure modes. Um, Two failure modes. One of them is like a splitting failure, and the second is like a pull-out failure. So let me just discuss at first the pull-out failure, where this pull-out failure happen when the surrounding concrete is well confined. There is a lot of like sufficient cover and transverse reinforcement rebars. The mechanism that is leads to the failure is that the reed bars are transferring the force through the shear forces along the concrete interface, or in the interface in between the concrete and um, reinforcement reed bars. So the concrete between the ribs is trying to shearing off progressively, and they are slipping out without like a major cracking. On the other side, the splitting failure that will be the content of today's session is basically the opposite. So it happens when the concrete is has some insufficient confinement. There is like a less amount of the reinforcement rebars. The cover is insufficient. So that's based on that, the concrete is mostly splitting off, not like a pulling out. So this is the once we talk about the mechanism, the bond stress generate the radial stresses. These stresses causes like a longitudinal cracks and the concrete trying to split out. Actually, there are some governing parameters, for the splitting failure modes. There is mostly dominant tensile strength of the concrete and cover thickness and the spacing of the reinforcement rebars. So once we double check the tabulated data coming from the CEB-FIB model code, we have like a clear insight what is the slip, permitted slip, and what is the maximal bond stress for pull-out failure and for splitting failure. Actually, the content of this session will be mostly dedicated to the splitting failure at this point, because there is some linear elastic behavior at the beginning. You are just reaching some point, and there is just a brittle failure that leads to the consequences as a splitting, and you can experiencing some progressive damage that that is represented by this dashed blue line. So this is mostly well fitting with the curve that will be presented actually right now. But beforehand, let me discuss some testing setup. In this testing setup, I just created, or we will create, the concrete cylinder with diameter 200 millimeters, height of the 200 millimeters, and there is like reinforcement bar with total length of the 200 millimeters, that half of the rebar is embedded inside the concrete, and at this region will be like a putting the cohesive traction, or some the properties for cohesive traction and damage separation law. So this is the setup. The bar has a diameter 20 millimeters. Okay, so let's talk about the traction separation law. So traction separation law, um, before we just started, I just prepared, just give me a sec. Okay, traction separation law. Let's discuss what is basically behind. So I will just describe what is happening inside a concrete volume. So once the specimen is subjected to axial force, that is in the reinforcement rebars, the reinforcement rebars is facilitated by the ript, where you can experience some mechanical interlocking, also the friction and chemical bonding in between um, those two mixes. So actually, um, this is the effects of this friction, chemical bonding, and the mechanical interlocking should be somehow like a transferred into the diagram, where in the vertical axis is like a traction, and the horizontal axis there is like a separation. So once we are talking about the splitting failure, that's very well accommodated to have like a linear elastic branch at the beginning. So once we like hit this damage initiation, at this point is starting progressively damage, and that's experienced by the decreasing of the stiffness at every point. So to start off with some traction, and to receive some like a traction stress, I need to have some stiffness metrics and the displacement. This is like those are the basics. So based on the stiffness metrics, you can see I am just having like a full matrix with I would say coupled of diagonal uh, terms that are actually contributing to like increasing or decreasing the traction, uh, utilizing some shear or yeah, shear in both direction. For example, once I'm talking about the normal direction, so once this off diagonal terms are not equal to zero, so I'm experiencing just the contribution of this off diagonal coupling terms to the complete normal traction. But in the standard scenario, we'll be mostly working with this diagonal stiffnesses. The off diagonal stiffnesses will be equal to zero. So basically, the stiffness matrix will be just diagonal matrix and will be simplified. Here will be the off diagonal will be represented by the zero terms. So in general, the interface is like a adhesive layer with the zero thickness because I wanted to represent the interface like that. There is like a zero thickness that this is what we can make as assumption. And from the traction separation law, at this I would say stiffness matrix, this is like there is no association of the damage, but it will be discussed later because actually right now we are talking about about this area from the point zero to point where the damage will initiate. So once I will move forward from this point, there will be some damage that need to be represented in the stiffness matrix using some scalar in the form of the damage. So, and how to identify that the damage will initiate? So there is like options or criterion that can be utilized. Um, There are four very well-known criterion that are used in between the community of engineers: maximum stress criterion, quadratic stress criterion, or maximum separation criterion, or quadratic separation criterion. So based on that, if you know you will fulfill what is basically in the bracket, it will be equal to 1. So you will hit this point. So once you are inserting the values of the traction or the slip, you are in the range in between the 0 to 1. So this is it works for damage initiation. So once you hit the 1, so there is coming the damage evolution. Damage evolution as a linear descending branch. So as you can see on the slip versus traction diagram, um, this is basically those are the data for our testing setup where the maximal stress on the damage initiation is 2.5 megapascal, and the slip delta zero is equal 1.8 millimeters. So from this point on, I'm experiencing some damage, and the damage need to be somehow described. How? It will be discussed basically in the next slides. But what is like a phenomenon that the traction is linear, but if I compare the slip versus damage, so the damage is like a hyperbolic function. Why? Because the delta max, what is basically the slip at each point that I will create, uh, so the delta m max is in the denominator. So it means there is like a 1 divided by delta m max. So this is the reason. And once I want to like describe the damage, I need to insert the damage and reduce based on the slip. I need to reduce the traction. So the damage is very important parameter that is basically driving your calculation. So once the okay, I will just erase it. So once yeah, once you reach this point, the damage will initiate, and the damage is coming relatively from zero at the damage initiation, where the coordinates or the point here has some t0 and the delta zero variables, and at the point of the fraction, the damage will reach uh, like a number one, that is like complete damage, zero stiffness. So you will observe some delta f and tau f. So let's get deeper and discuss it a little bit more. So let's approach to damage evolution and the derivation of the damage for linear traction. Actually, you can coming out from the equation of the line. So we can just start off with the equation of the line in general, and once you substitute some, I would say, variables in the equations in the numerator and denominator, you can just describe this curve, this descending branch. So what you wanna do actually, once you double check what is happening here, y is like traction, and x is basically the separation. So once the x is equal to delta max. So those are the steps that you will be like iteratively increasing. The y, once you increasing the x, or in general delta and max, you will be obtaining the tractions, some decreasing of the tractions. So the x1 is equal to delta m0. So x1 is basically here, delta m0, and y1 is like a t0. So we are here. This is a t0 at the damage initiation. x2 is equal to delta mf. So this is the slip at the point of the fracture, and y2 is equal to 0 because the traction is equal to 0. So once you complement the equation, you will receive basically those two terms on the left side and the right side of the equation. Actually, at first we need to simplify the right hand side. So what we can do, there have been like a 0 minus t0 is equal to minus t0, so we can just do some adjustment, and we will multiply both sides with this term in the denominator. So you will remove the element from the denominator. So this is my equation that I'm observing right now, because my goal is to get like a clear view about this t with the dependency on the delta m max. So once I will do some algebraic adjustment, um, I can get the equation that looks like that. So actually, I will just move this t0 on the right side, and once I have twice the double t0, I can just simplify that and put it in front of the brackets. So there is like a t0 is equal 1 minus delta m max minus delta m 0 in the fraction, and it's divided by the delta m fracture minus delta m at the damage initiation. So this is my delta m max that is like described, and based on this equation, once I put the parameters, so I will be receiving what is basically happening from the damage initiation point from the sense of the traction. So I need to just substitute the number one uh, over like using some, I need to put everything over one denominator. So I will do this algebraic adjustment. So once I will do that and put it inside the equation, and I will combine the fractions. So I need to just put it into the denominator. They'll be like merged those two elements into the denominator. So I will be receiving something from the point of view of the slip, what is on the left side, and something what is from the point of view of the slip on the right side. So there are some coincidence that minus delta m0 and plus delta m0 can be cancelled out. So what you will receive once you express the t delta m max, you will receive that t0 times delta m fracture minus delta m max divided by delta m fracture minus delta m at damage initiation. So this is some adjustment of the equation where you can see what I did, and we are approaching to when does it make it like a physical sense. You need to always double check the boundary conditions. So I mean, once you put what is happening at the damage initiation, so it means that your delta m max is equal to delta m0. So once I insert it into the equation, I will receive that my traction is equal to t0. So that's fulfilled. Actually, at the failure point, I need to just put the boundary condition in the form that delta m max is equal to fracture separation. And once I will do that, the fraction will be equal to 0. So my assumptions are correct. So I can proceed to the final boxed results. And this is how the traction will work. At the part where the damage is activated. But right now we are missing the damage. So we need to come back to the basics, and we need to just say that basically the traction in the damage is equal to this equation. This is the equation that we expressed in the previous slide. Yeah. And how you will describe this T damage in the other form. So in the other form, you can just describe this T damage as K time delta m max. So once I will express this T delta T with I would say this elastic stiffness and this delta m max, I put in front of it the 1 minus d. Once I will do 1 minus d, so once the d is equal to 0, it's like a k time delta m max. So you're at the point at the damage initiation, and it will be your traction. Once the damage will be equal to 1, you will receive 0, what is basically the point at your failure mode. Okay. So actually, let's get isolated this 1 minus d. I can express that k time delta m max is equal to t0 divided yeah, 1 minus d. Yeah, once I will just take those those two variables, and I will put it on the other side. I will receive this equation. So, and I need to like extract this and isolate this damage. So once I will do some key substitution that T0 divided by K times delta M max, it's this part. So once I will like extend it with a K, so I can delete the I would say dependency on the stiffness actually. So you will just simplify the solution that 1 minus d is equal to this part, this fraction, this ratio, and I can move it forward. So once I will just be solving this d, because before there's been 1 minus d, so I can just put it on the other side. And once I put everything over a common denominator, basically under one denominator, I will just extend this number one with this part, put it on the top. So once I will expand this numerator, I can notice that there are some, I would say, elements or variables that can be canceled out. So once it's been like a cancel out, there are some delta M fracture that are the same. So I can just put it in front of the bracket, and those two members put it to the bracket. And based on that, I will receive the damage with the dependency just on the separation, and I can very well describe using those two, I would say, inputs, and control the separation. So that's been basically it for from the first session. I will just give some point that I've been endorsed as a authorized and certificate trainer for Idea Statica. So once you have a problem or struggling with some connection, concrete details, so do not hesitate, and just request the meeting over the Struck Insight at gmail.com. I'm also actively participating on the LinkedIn, on the social network. So once you wanted to follow me with for more content, you can just follow me. This is my page. In the next session, I wanted to focus on the modeling part, where we'll tackle the testing sample in the ABAQUS, and we will do step by step. I would say modeling procedure from the part over the material, assembling, boundary conditions, and mostly we will get deeper how to insert and how to compare the built-in damage evolution law with your predefined damage, and we will be trying to get the match in between the inbuilt and like a user-defined damage. So once it will be like content of the second session. So thank you for your attention, and if you like this session, so feel free, and do not forget to subscribe the channel for more valuable content. Thank you so much.